There we go. When we do transformations on all kinds of functions, you're going to see them on graphs a lot of the time. But before we get into it, we just need to remind ourselves what a function is. So there is a part of a Math 10C unit where you define functions. Okay, so like, what is a function? A function is something that passes the vertical line test. Passes the vertical line test. I'm not sure if that's how you spell vertical. That sounds right? See, that's why I wouldn't do an English Kahoot, that's for sure. Vertical line test. We're going to call it a VLT. That's what you'll see it as short. VLT. I don't think we even talked about this in Math 11. Everything we did in Math 11 was a function, so we never really discussed it. In Math 10, you would have seen these things and been like, is this a function? Is this not a function? Okay, and you would have performed something called the vertical line test. So what you do is you take a graph. I'm just going to draw a random graph. Let's start with a circle. Okay, so there's my little graph. The vertical line test is, can you draw a vertical line on that graph and touch the graph in more than one spot? So for instance, if I drew a vertical line right here, there's a vertical line. It is touching the graph in two different spots. It is touching once here and once here. More than one spot. That means this thing failed the vertical line test. Because it touched in more than one spot. That is not a function. Let's try another one. So something you saw a lot of last year was graphs of something called quadratics. Quadratics look like this, right? They have like one bend to them. That's a quadratic. If I said, is that a function? You would do the vertical line test on it. Is there anywhere on that graph that I could draw a vertical line and it touches the graph more than once? Not possible, right? And if you're not sure, like you can just like run your pencil across it, right? Like if I run my pencil across this, am I ever touching the graph more than once? My pencil's a little small to be doing that. Oh, that's good. Did my computer die? Did it die? Nope. Just Google. So like if you ran your pencil across your paper, I'll run a ruler. Like, am I ever touching this graph more than once? And it's always touching at one spot, like it's touching right here, right? And it's just touching at one spot all over. But it's never touching more than one spot at a time. That is passing the vertical line test. That passes the VLT. This is a function. You remember that from Math 10? Yeah. It's a long time ago. And you really talk about it like once and then don't ever talk about it again. Yeah.
This is a stupid question, but like, will you ever have a scenario where in one spot it touches once, but in another it touches twice?
So, if you had something like this, that's not a stupid question. That's a great question. Nailed it. So if you had something like this, maybe it's like going up, then it kind of backtracks, and it goes up like that. Yeah, like a function like that. In certain spots, that passes the vertical line test, right? If I drew a line right here, that passes the vertical line test in that spot. But if I drew a vertical line there, it now fails the vertical line test. And if it ever fails the vertical line test, that is not a function. This touches 1, 2, 3 all at the same time. So even though it passed on this side, once you move the vertical line over, it then failed the vertical line test. That is not a function. Cool. Most things that we see are functions, just for the record. It's pretty rare that we have non-functions up until this class. Okay, we'll start to get things that are not functions. But everything you've seen up until now was a function, pretty much. Like I can't even think of something in Math 11 that wasn't a function. Everything we did was functions. If something's a function, that means we can write it a certain way. So how can functions be represented? The first, I'm going to write out different things you can do, but I'm going to do this. Something like that. Okay, that's called function notation. I remember like way back we used to always have like y equals, and then it changed to f of x equals. The reason it changed is because you then were only dealing with functions. When it was y equals, its potential it wasn't a function. By seeing this, it tells you you have a function. Okay, that is a function. That's called function notation. What is a function? No, you're right, Kenny. Like I see what you're saying. Like what is a function? Like I didn't really answer. I just said how to tell if something is a function. I never said what. Yeah, that's fair. Like what is a function, Mr. Kennedy? You're not helping me out here. And then I showed you how to tell if something is a function. I never actually defined what a function is. A function is something that changes depending on a variable. So, for instance, like you've seen functions all the time. You've seen things like this. Yeah, like this changes based on x. So we call it a function of x. Whatever happens to x tells you what happens to y. So that's what a function is. By changing one thing, it gives you a different thing. Yeah, and you would have then seen this written like this. And what you're saying is like your result or your output is a function of whatever x equals. So if x equals 1, you get a different answer. If x equals 2, you get a different answer. Right? This result is a function of whatever you choose for x. What is a function? And so then you can graph them, right? Like this. And that's how you tell if something is a function or isn't a function. Function notation is one way to do things. You could also just draw graphs. Right? So I could represent functions with pictures, graphs. Those are the two main ways. You could also do like a table of values. If you don't know what a table of values is, so a table of values would be something like this. Right? When x equals 1, y equals 3. Right? That's a table of values. When x equals 2, y equals 5. Right? So on and so forth. And technically, I mean, we don't, again, do it often. It is going to happen more this semester. You could use ordered pairs to represent functions. An ordered pair is like this. Right? It could be a way of me showing a function. Ordered pairs. What I'm saying is when x is 1, y is 3. When x is 2, y is 5. Right? Cool. What we're going to do in this unit is we're going to take functions, we're going to move them around. So we're going to change them. It's called transformations when you look at it graphically. You're physically moving things. That's why we call it transformations. But we also can do transformations on function notation, on table of values, on ordered pairs. So you can do it in more than just like a graphical way. Graphs are just the best way to do it. Types of functions. Seen all kinds of types of functions. Yes, sir.
Can we not do the one where we use the brackets and the? We learned to make functions. I just can't remember what it's called. Yeah.
Set builder notation. We're gonna have to. Yeah, I mean, I can't just avoid it. It'd be nice though. It'd be nice.
It's easier.
Yeah.
I think it's so much easier.
Like when you just use a bracket instead of like the full thing.
Well, yeah, you do like. So
It's
like
way. Yeah. We'll do that. That's way nicer. Yeah. Types of functions. So these are types of functions we've seen linear functions. That means it just makes a straight line. They're so excited about domain and range over there. I don't know. Okay, so we've seen linear equations, right? This is math 9 / math 10, where you just got straight lines like that. You then did quadratic functions. So quadratic functions look like this. They give you like that one curve. And that's a lot of math 11. Then you could do something called a cubic function, which if you took math 30-2 with me, you've seen it. If you haven't, then you probably didn't see them a lot. It's when your degree or your exponent is 3. Then you get graphs that kind of look like this. They kind of like give 2 little bumps and then go. We'll see more of those this year. You might have seen it last year, but doubtful. We have radical functions. So that's if you have the square root of something. Radical functions typically look like this, like a little curve. Thank you. You have something called an absolute value function, which you would have seen for about 10 minutes in Math 20-1. You did it in like the first unit for one example. And it looks like this, like it's got these bars on the side of it. Basically just turns anything negative positive. Again, we'll do more of that in the future. But the graphs look like this. These are functions, right? Because I would pass the vertical line test. Makes like a V. It's kind of cool. You did rational expressions and rational functions, which meant fractions. All right, so last year you would have seen a lot of that. You did a whole unit on it. It creates these weird graphs like this with those weird asymptotes, right? You should have seen those last year. We did a couple last unit. We did log functions. Remember when we graph a log function, it like falls over. It looks like this. We did exponential functions, which are like the opposite. So they just go up really fast. They look like this usually. And then we haven't graphed them before, but we will do some trigonomic functions as well. So we'll do sine and cos and tan, which sine and cos look like this. There's no example of tan because it's a disaster. But sine and cos make a cool little wave. Those are all functions because they all pass the vertical line test. So every one of those pictures passes a vertical line test. Beautiful. Now let's do some transformations. What is a transformation? So, transformation. We are going to take graphs and we're going to move them around. When you're moving graphs, though, you're technically changing and transforming the equation, and you're transforming the ordered pairs, and you're transforming the table of values. You're transforming everything, right? We always show you the graphs because visually it's like appealing. You can see it move. But technically, you're doing a transformation to every little point on that graph. So you're going to have to know how to show that and demonstrate that as well. Today, we're just going to do vertical and horizontal, left and right, up and down. Bueno? Bueno. Looks like this. So you're going to have y equals f of x. And then instead of it just stopping, you then have this thing that says minus h. And then it closes the bracket. And then you have something outside of that that says plus k. Perfect. H is the horizontal translation. That h tells you if you're moving left or right. Left and right. The k that's outside of the brackets in my function notation is a vertical translation. K is moving things up and down. Perfect. What those things are doing is they're taking every ordered pair and every point and they're moving it. To show how they move every little point, we use something called mapping notation. If you're moving something left or right horizontally, then you're changing the x value of something. So in mapping notation, that means your x value would change by whatever h is. So if h was 2, then every x thing would then go over 2. So it becomes x plus 2. If you're moving something up or down that's vertical, that would be the y value is changing. In mapping notation, that means that the y value goes up or down, whatever that k is. Again, if k was 2, that means you went up or down 2 units. And it's mapping notation. Yes? Okay, let's look at some examples to help. So example 1, describe the transformation applied to y equals f of x. The first question is this. Y equals f of x minus 3. If you think about your general form, this is your general form right now. Agreed? X minus, it's minus, yeah, minus h plus k. We have this. Right? That means they gave us an h value. Oh, I want to do that in red, not purple. Sorry. And what does h tell us we're doing? H value is a horizontal translation. So left or right. That's what h is doing. Perfect. It's opposite of what it looks like. So usually people would think minus means you move left, right? When you have minus 3, that actually means that you went 3 units right. It's the opposite of what like intuitively you would think it is. The reason it's the opposite is because the negative is part of the form. The h value is actually 3. So I do want to make that very clear. Like h in this question is 3. H is not negative 3. That's why I went to the right. Yeah, no. I'm going to go back and do like that little log thing after. Go to B. So if I'm looking at B, what's the h value of B? Negative 2. Right? Because the form has the subtraction sign. So somehow this became plus 2. The way it become plus 2 is if I had minus negative 2. Minus a negative turned it positive. H is negative 2. Perfect. In layman's terms, what does that mean? Layman means like just casually speaking about something, right? So what is going to happen to this graph if H is negative 2? Where would it move?
To the left.
To the left, right? So negative 2, it went 2 to the left. Now that's like just speaking about it. You do have to write it mathematically, like properly. So let's talk about like the terminology you have to use. You couldn't just say 2 left. Like if we were talking about it, sure, say 2 left. But when we are actually writing it out, this thing had a horizontal translation two units left. From my understanding, they are very picky about that. You must use the full like sentence. You cannot just say 2 units to the left. you have to say it's a horizontal translation. That means left or right movement, 2 units to the left. Very picky.
Translation, not translation.
Translation. Transformation means something's moved or it's transformed. Translation means that it's actually like physically slid left, right, up, down. So for instance, like transformations will also do like stretching is a transformation. So when you're moving left, right, up, down, it's a translation. Do you remember that from Math 1? A little bit? No? Quadratics? We did this with quadratics, and it was basically the exact same. So if you look at C, what value is there? Is it an H or a K? That's a K value. Perfect. What does K equal here? K equals 4. My computer is not going to let me write. All right. So this is a vertical translation. Vertical translation. That means it's shifted up, down, left, right. Because it's vertical, that's up or down. Vertical translation 4 units up. Okay, so when K is positive, you're going up. Looking at D, what's the K value for D? K is -6, perfect. That means it's a vertical translation because we have a K value. Vertical translation. Six units down. Because it's negative, it went down. Yeah.
So if it's a horizontal translation in the brackets, will it always be the opposite of what it says?
Yeah. So, and that's what gets people like messed up, right? It's like the H value is the opposite of how it looks. So like it looks like it's +2, it's actually -2. And because it's negative, it's going left. And that like throws people off when we're talking about like what's the actual H value versus like when I'm looking at it, what's the H value? Okay, that's how you would show transformations, translations in function notation. Let's talk about what it actually does to the function. So let's go back to A. I have y equals log x. What this means, when you see a horizontal translation, you need to take all your x values and subtract it by 3. I like to think of it as you replace x with x minus 3. So I'm going to go to the equation and I'm going to replace x with x minus 3. So my new equation would look like this. Y equals log. Instead of x, I write x minus 3. That is your new function. It has gone 3 units to the right. It's like substituting, essentially. Yeah.
Say we're graphing an absolute value. How do you do that?
It's under the math function. There's something called ABS. That means absolute value. So if we looked at this one is telling you to change x with x plus 2. So every x value is going to get 2 added to it. So you replace x with x plus 2. So it now looks like this. Y equals the square root. Instead of x, it's now x plus 2. And what I've done is I've taken that equation or that original graph, this graph would shift it 2 units to the left. So if I graph this and I graph this, it would be 2 to the left. Yeah.
When you transform these and put it in the calculator, where you show the same.
Yeah, so like if we tried it, can you see my, you can't see my calculator, give me 1 second. Let me pause that video because horizontal things are actually harder. So vertical things are easier to put into our calculator or put into our equation. So when you look at something like this,
Why is mine winning?
did you put -3? Minus or negative? Vertical things are actually easier to do. The horizontal ones are hard. You actually take the x and you replace the x. With the horizontal, the vertical stuff, it's much easier. So essentially what they're saying is you take the function, so whatever that function might be, and then just add 4 onto the end of it. So if the function was y equals absolute value of x, that's what that is. Now you take that exact same function and then add 4. Just like add it onto the end of it. Original function, add 4 to it.
How come it doesn't go in the lines with it?
Because it's if you put it inside the lines with it, that would then be a horizontal translation because you're changing the x value. By adding the 4 to the outside of it, you're saying do the original function and then add 4 afterwards. So this one, like same idea. Like take the function and then subtract 6.
Wait, how do you do absolute values?
Don't worry about graphing those. We will graph those later. I'll show you guys how to do that. So you got y equals the original function and then subtract 6 from it. Just tag it onto the end. Much easier. Awesome. That's translations. We've already kind of done a graph, but let's do a graph and let's talk about it a little bit. So given the function y equals f of x, determine the position after the function has been transformed to this. So it started as y equals f of x. And then it's been transformed to become this. Started as f of x, turned into that. What two values do you have here? You have an h and a k. Looking at this equation, what does h equal? Yeah, h is 2, right? It's this one. Remember, it's not -2. It's the opposite of how it looks. What is k here? Perfect. K is 1. This means that you have gone 2 to the right and 1 up. In layman's terms, like speaking just casually about it, that's what's happened. 2 to the right, 1 up. They're saying this is y equals f of x. You now need to create this graph. So take this, move it 2 to the right and 1 up. I like to pick like important points. So when I'm moving something, if you pick these points and move just those points, then you can connect the dots and make the exact same graph. So I need to move each one of those points 2 to the right and 1 up. This red dot, 2 to the right, 1, 2, and 1 up would be right there now. That'll come back.
Wow. Nice.
Nice. That's embarrassing. It's probably Miss.
It's this one over here.
That's funny. So 2 to the right, 1 up. The red dot is moved. Do the same thing to the purple one. 2 to the right, 1 up. It would be there. Do the same one to the green one. 2 to the right, 1 up. Do the same to the blue one. 2 to the right, 1 up. And then if you connect the dots, you have the exact same graph, but the whole thing is now moved 2 to the right and 1 up. Done. Just for the record, when you see graphs, like they usually say what the graph is next to it. So this graph was y equals f of x. This new graph was y equals f of x minus 2 plus 1. 2 to the right, 1 up. Bueno. 2 questions over done? Oh, no, 2 slides over there. Okay. The point, 2 comma negative 3, lies on the graph y equals f of x. Determine the coordinates of the point after the following transformation. So we started here. Start. So we started at 2 comma negative 3. That was on y equals f of x. Now we have this. Perfect. What has happened? The original graph had no h value. Now it does. The h value is negative 7. So that means h equals 7. The original graph had no k value. Now it does have a k value. It has a plus 5. That means k equals 5. So the original graph to the new graph has gone 7 right, 5 up. Is everyone okay with the fact the original graph has moved? It's moved right and then up? Perfect. I don't know what the original graph is. I don't know what the original function is. All I know is 1 point on that original graph. That point is 2 comma negative 3. I now need to know where that point went. That point went 7 to the right, 5 up. The way you would show that, it went from 2, negative 3. That's an arrow. A bad arrow. That's an arrow. X values are left and right. Y values are up and down. That means my new point would be 2 plus 7, because I went to the right 7. And my new y value would be negative 3 plus 5, because if I'm going up, I would be adding. My new point is at 9, comma 2. Some people draw a picture and you could move the point. I'm sure that works. But this is a nice quick way to just do it, right? X's are left, right, Y's are up and down. Nice and fuzzy for you, so it's easy. We're good with that? Yeah. H's to the X, Y, K's to the Y. All right, let's look at determining the equation of a function after vertical translation. So, determine the equation of the function f of x equals x squared plus 4x after a vertical translation. Vertical translation, 5 units down. Vertical translation is a k value. It went down 5. That means k would be negative 5. Agreed? Perfect. That means you started with this. You started with f of x. Means I am now doing f of x minus 5. They want you to take the function, go down 5. When you're doing vertical changes, you just add it on to the end. So it started like this, f of x equals x squared plus 4x. That's how it started. And now I'm doing that same function, but I'm just subtracting 5 from it. That is my new function. I went 5 units down. Can't tell if it was too easy or too hard or too confusing. That one's a little tricky, right? Because they actually gave us a function. And they're asking us to show what it would look like if it went 5 units down. The next one's harder, so I want to make sure we're good with that before I go. Are we all right with adding that, subtracting that k value? Just like putting it on the end of the function? Okay, the horizontal ones are trickier. So the next one says, determine the equation of the quadratic, f of x, so same function, after a horizontal translation of 2 units right. Horizontal translation 2 units right. They are talking about your h value being 2. It would look like this. You started with f of x.
Wouldn't H be negative?
It's positive 2 because I want to go to the right, but when I put it into my equation, it turns negative. So it looks like this. X minus 2. Like that. So it looks negative in function notation, but when I speak about the h value, it would be positive 2. Those horizontal ones are messy, right? Because it's like the value changes from positive to negative. I haven't done the function yet, but is that okay? Yeah, Joe.
Sorry, going back to the other one, if we're going to do a horizontal translation on that f of x, how would that work? Or are you just going to?
That's what I'm going to do right now.
Okay.
Yeah. So I'm going to do a horizontal translation of negative 2.
Yes.
Yeah. But are we okay with this idea? That h was 2? That means I want to take my original function and I want to do this. That means that you take your x value from your original function and you change it to become x minus 2. It's like you're substituting x minus 2 in. So it started like this. Y equals, sorry, I'm not going to do y equals. F of x equals. It started like this. And now you want to take your x's and change it to be x minus 2. So it would now look like this. X minus 2 squared plus 4 times x minus 2 instead of just times x.
Would you leave it like that, or would you factor?
You'd have to multiply it in.
Would you get like the x squared and 4x?
That's the original function from the start of the question. Sorry.
Um,
We're still talking about the same one from the very first part of the question. That's a good question. Sorry, I should have probably clarified that. Yeah, that makes sense now, yeah. Yeah, we're just doing a continuation of the first question. Yeah, no, we're not doing the vertical one now. We're just doing the horizontal one. So notice that I actually changed x to be x minus 2. Perfect. I wouldn't leave it like that. So that was immediately this question. I would multiply this 4 in. Okay, so you'd actually expand that. You could also expand that squared too. So you could rewrite it in many different forms, right? Most likely you'd see it like this. Actually, they would expand that too. So you would do this x minus 2 squared. So x minus 2 squared would be x squared minus 4x plus 4. Foil, right? We don't just put the squared in. It'd be x minus 2 times x minus 2. You foil it. I see people looking at me like I'm crazy. X minus 2 squared is x minus 2 times x minus 2. So x times times negative 2, negative 2 times x, negative 2 times negative 2. That's how I'm getting this. Do I look less crazy now? Okay, just needed to see a little visual reminder of where things are coming from. And then you would also multiply in that 4. So this 4 would come in the brackets. To be plus 4x minus 8. Then collect your like terms. This thing now, after a horizontal translation, would be x squared minus 4. Collect like terms, right? So the negative 4x and positive 4x would cancel out. And then 4 minus 8 would be negative 4. Looking at me like I'm crazy again. Did I mess something up? Do you see me? I'm combining like terms, yeah? So like minus 4x plus 4x cancels out. Plus 4 minus 8 is minus 4. Yeah. Yeah, it was a long week off, eh? Cool. This represents a function that then just went 2 units to the right. That's way harder. The horizontal translations are way harder.
So with the vertical one, you always just throw it at the end.
Throw it at the end. Yeah, the vertical ones are so much nicer. Right? So a vertical one is like just add it on. Whatever it is, just add it on to the end. In this case, subtract it on, but same idea. Those horizontal ones are the tricky ones. It's because you're literally replacing x with something else. Much more complicated. Okay. Last one. Determine the y-intercept of the equation y equals 2 to the power of x plus 3 using 3 different strategies. We're going to do it graphically, algebraically, and using transformations. That is not... Yeah, no, that's right. It's like, that's missing something. Yes, no. I see what it's asking. Let's do algebraically first, because that's the easiest one. How do you algebraically find the y-intercept of something? Yeah, good. I did teach you something last unit. Right? If they ask for the y-intercept, that means x equals 0. So algebraically, that means go to your equation and change x to be 0. That means 2 to the power of 0 is 1, plus 3 is 4. My y-intercept is at 4. I find algebraically is the easiest way to do y-intercepts. If you want to do it graphically, you just throw that in your calculator and try to see where that y-intercept is. So in your calculators, you would put into your y equals, you can't see my screen, can you? 4% remaining. Oh boy. I'm getting warnings from my Chromebook. So put in your calculator, 2 to the power of x. Is it plus 3? Like that. Perfect. Just use your standard window. So it would be negative 10, positive 10, negative 10, positive 10. Mine's positive negative 5, but I mean, it should look the same. You should see a y-intercept. It's right there. It's at 4. If you want to make sure it's at 4, there's different ways of doing that. What I do is I hit trace, and then 0, and then enter. Trace lets you tell your calculator X values. So trace 0, enter. The y-intercept is at 4. That's how you graphically would do it. Gorgeous. Get rid of that thing. Give me this thing. I have to slide over. So, we're not going to get through this transformations without my computer dying. Okay, let's do transformations. So how can you find the y-intercept using a transformation? The way you could do it using a transformation is you could create or try to find like the original function and then what's happened to that original function. So for instance, I could pretend or imagine that this is the original function. And I know the y-intercept of that original function. That's an exponential function. Do we remember where our y-intercepts would be on that? Yeah, our exponential functions from last unit, they all had the same y-intercept. They all had a y-intercept of 1. That came from last unit. Our exponential functions, y equals something to the power of x. The y-intercept is 1. That was like our random exponential fact that we knew from last unit. Then I could imagine that this plus 3 is a vertical translation 3 units up. So I looked at this. I knew the y-intercept was at 1. I looked at this. I knew it was a k value, and it moved my graph 3 up. That means the y-intercept would have gone 3 up. 3 up from there would be y-intercept is at 4. That's tricky. Tomorrow we'll do this next question as like a review of translations, and then it is going to get kind of hard. So I would practice translations tonight so that when we get to the harder stuff, it's not so hard.